Join the conversation.
Join the conversation.
You're with Cape Talk.
Welcome back. It is 9:34. Views and News through till 12 and me, Clarence. And don't forget, we have that appointment with the Naked Scientist right now. Welcome, Dr. Chris Smith, lecturer at the University of Cambridge. It is great to have you with us on this Friday morning.
Good morning, Clarence.
Here's a question about politics and science. And I'm not sure the two go together, Dr. Smith, but maybe I should ask it. In fact, I can't find it. It's gone. Maybe it's a good thing. Because there's nothing scientific about politics now, is there?
Well, apart from the fact that without governments, we don't have a strategy and a science policy, and we don't have decisions being made around health and that kind of thing, all of which are informed by science. So, yeah, I suppose there's no connection between politics and science. I'm just being facetious, of course. That they are bound up, but for all the reasons I've mentioned. And if you think about the recent pandemic, when we needed the whole world to work together in order to come up with strategies and solutions, both public health strategies, but also things like vaccines, you need governments talking to each other to orchestrate literally billions of people and their combined actions to combat these things. And if you think about the biggest threat we're probably all facing now, which is climate change, you need an international solution to an international problem in order to do that. And you do that politically. You do that by interacting between countries and within countries, and that comes down to politics. So I think science is very, very political.
Okay, let's get on to some of the other questions. Morning, Dr. Chris. Having lived in the UK for many years, up and until recently, I followed Michael Mosley's broadcasting career for a very, very long time, as well as the Naked Scientist podcast. I'm sure, Chris, he must have been a friend of yours, and so I wanted to send my condolences on what is a very sad loss to the medical fraternity, says M.
Hi, Em. Well, actually, I did know Michael, and I went out to dinner with him, not last summer, the summer before, with another broadcaster, Jeremy Vine, who we made a pact at the start of COVID. We said, when COVID's over, we're all going to go out to dinner, thinking it would be a couple of months away. And it took 2 or 3 years before the pandemic was over, and then we could all go out to dinner. And so, yes, it was very, very poignant when we saw what happened to Michael Mosley to think, you never know what's around the corner. And I was only saying this to members of my own family just the other day. You don't know what's around the corner, so make sure you make the most of every moment.
Indeed. There's a voice note or two in. I'm going to allow Joe to play in one or two of them. Joe, let's take a listen.
Good morning, Clarence. My question to Chris is, for how long does hyperglycemia in excess of 11.1 millimoles per liter have to be present in the blood for it to exceed the renal threshold? The reason I ask that question is that I sometimes see patients with sort of high sugar levels of, say, 15 without glycosuria, and then other times sugar levels of 9 with glycosuria, and I can't find the explanation as to for how long hyperglycemia in excess of 11.1 has to be present to result in glycosuria in the absence of SGLT2 inhibitors, of course.
Thank you for that question. What's being referred to here is that when a person's blood goes through their kidney, everything in the blood, with the exception of big molecules like proteins and huge things like cells, gets filtered out because the blood vessels in the kidney are like a sieve. And the kidney then brings back into the bloodstream the stuff that it wants and allows to be thrown away the stuff that we don't want in the body. So it pulls back in sugars, glucose specifically, but also amino acids, salts, and certain other things. And these are selectively reabsorbed using a transport system that uses energy to grab the stuff it wants from what's been filtered out and pull it back into the bloodstream. Now, when you've got an energy-dependent process like that, it means that there is a limit because of how many of the things that there are capable of pulling the thing you want back into the bloodstream that there are on the cells. And this is what's being referred to here as the glucose transport maximum. You filter out sugar, glucose, and then you use transporters to pull it back in. And there's a certain number of those transporters. So if there's more sugar in the blood and therefore being filtered out of the kidney, then you have transporters capable of grabbing it. You end up with some being left behind and being thrown away, and that ends up in the urine, and that's what causes what was also referred to as glycosuria. or glucosuria. And this is where a diabetic would have sweet urine, hence diabetes mellitus, the name from the old days, sweet urine. And we can detect that using a glucose dipstick, which you put into the urine, and it can register the presence of glucose. Now, different people will have a slightly different threshold for that happening, and different people's tubules, the things in the kidneys, also differ from each other. So there is some variation around an average of about 10. So if the sugar level goes above about 10, then you start to lose a bit of sugar into the urine. But remember, you're going to get spikes in blood sugar all the time. And sometimes you will therefore lose a bit of sugar in the urine, but the amount is going to be tiny compared to the enormous volume of normal urine that's being produced. And the tests are sensitive only to a certain level. So unless you use laboratory grade tests, you're going to potentially miss some of the sugar. And also there is a bit of variation between people and even within a person's own kidney. So all these things add up to variability and variation in the process. And it's the sustained elevation of blood sugar that leads to the sustained loss of sugar in the urine, and therefore a build-up that can be detected because it's above the threshold of a lot of these tests that we tend to pick up on. So really, the bottom line here is it's a good healthy diet and good sugar control if you are diabetic for the most part, but understanding that everybody's blood sugar, even a person who isn't diabetic, will peak at high levels transiently before the various mechanisms we have, and insulin foremost among them, kicks in to rein it in. But there will be periods when you do lose some sugar in your urine, even when you are not diabetic.
And of course, our half hour with the Naked Scientist, Dr. Chris Smith, lecturer at the University of Cambridge. Dr. Chris, why is yawning contagious?
Well, we think, and this is obviously a gross theory, but we think this has an evolutionary explanation in the sense that when we tend to yawn is when we're tired, obviously, and we tend to get tired when it is dark and when we've got sleep deprived. And that's one argument of that, is that sleep deprivation increases brain temperature, and yawning is a mechanism to cool brain temperature. So why make the process infectious? Well, the argument goes that if you've got a group of people, and we think about our primitive ancestors, they're in Africa somewhere and they're sitting around in their camp in the evening and in their community, and everyone's feeling a little bit tired after a long day, but there is a nasty thing trying to creep up on them and turn them into dinner. Well, if one person's feeling sleepy, it's likely that everyone's feeling a bit sleepy, and therefore everyone could miss the nasty thing creeping up to try and eat you. So if you make yawning contagious, everyone wakes themselves up a bit, which increases the vigilance of the entire group. So everyone is more likely to notice the thing that is trying to creep up and eat them, and therefore someone will probably be awake enough to sound the alarm, and that benefits everybody.
Okay, let's go to Joe. Joe's got a metaphysics question via WhatsApp.
How's it, Chris? Big fan, yeah. I just want to hear your take on something. You know, recently I've just been introduced to the world of philosophy and especially metaphysics, and it's not something I've normally contemplated, but I've been blown away. My mind has been blown by Immanuel Kant and his concept of things, what he calls things in themselves, and how he claims they'll be forever unknowable to human beings. You know, like, for example, what he says is, like, when we look at a tree, we'll never know what that tree actually is because we just synthesize it through our senses. And what we visualize, and that's all science for that matter, is just what we visualize, and we'll never know the true reality of those things. I want to hear your take as a scientist on that whole metaphysical concept of things of themselves versus what we perceive. Thanks.
Wow.
Yeah, I mean, I'm not a philosopher, and this is not my massive area of expertise, but I was having a sort of similar conversation with someone the other day because we were talking about our brains and how what I call a certain colour or a certain sensation, or I hear a certain sound and experience a piece of music a certain way, and I have absolutely no idea if what I see in my mind's eye when I look at a picture or I look at a tree or I hear a bird singing, if that's the same experience that another person's having. And if my dog looks at the bowl of food, is he seeing the bowl of food, albeit with slightly different colour vision, than I am? Or are our brains creating an entirely unique and different representation of the world for all of us? But at the bottom line is, it's still the same chemistry, it's still the same physics across the universe. And someone wrote to us the other day and said, well, would the periodic table that an alien has up in their chemistry classroom be the same one that we have? Would they teach the same physics in their physics lessons? And the really humbling thing here, and the amazing thing, is that the answer is yes. It doesn't matter where you are in the universe. It wouldn't matter what alien race you're part of. You're still going to have the same periodic table on your chemistry classroom wall. You're still going to have the same laws of physics, albeit not invented by Newton, but by some other alien who spotted the same relationships, because there are some aspects of the way that the universe works which are ubiquitous across the universe, and they will exist whether or not we're there to interpret them. On the other hand, music, things we create, that's music to us. It's music to a bird that sings, but it wouldn't necessarily be as meaningful to a different organism. So there are some things which really are hard and fast. They exist whether we're here to appreciate them or not, but there are other things that definitely don't. And our brains create an experience for us which we appreciate, but I can't compare my experience to your experience, and I find that really quite humbling.
Dr. Chris, would Weserbier be able to survive on Mars? And have we already contaminated Mars already, maybe with microbials, so introduced aliens to Mars?
I don't know what the first thing was that you mentioned. What's that?
I think it's white beer. I think it's
Yeah.
white beer. Weserbier, yeah.
I have no idea if that would be any good on Mars. And Mars is a horrible place. And the atmosphere is very, very thin, dominated by carbon dioxide. The temperature very, very low. It barely gets above freezing, if ever. And so your beer would certainly be cold. So the Aussies wouldn't be able to have a go at us English for warm beer on Mars, because it would be cold if you had it outside. But in terms of what we're doing to our solar system, yes, this is a really big concern. And it's very high up the agenda at various space agencies, because we're very concerned that we don't pollute space. And not just with our rubbish. There are thousands of pieces of space debris now knocking around in Earth orbit and beyond. But in terms of seeding life across our solar system, we have to be really careful, because when we're going looking for life and the origins of life, the last thing we want to do is end up detecting life that we put there by accident. So when craft are made, especially probes going to distant worlds, there is enormous rigour employed to make sure that those craft are built in as sterile a way as possible and are not contaminated with things that might lead to life ending up where it shouldn't be. So they do go to enormous, extraordinary lengths to try to make that the case. We used to think that space was such a horrible place and such a hostile environment that life wouldn't survive there anyway. But we've had to reevaluate that in recent years, because it turns out that there are microorganisms which are extremely resilient and capable of surviving in even the harshest conditions. And not even just microbes, even bigger organisms like tardigrades are so good at surviving in horrible environments that it is a realistic prospect that, given the right environment, if these things found themselves there, they could easily begin to flourish. And I remember doing an interview with a guy, Miroslav Radman was his name. He published a paper in Nature about 20 years ago, and he was studying bacteria that live in the Atacama Desert, and they're called Deinococcus radiodurans, these bacteria, and they were called radiodurans because they were found to be so resistant to radiation that no one could believe they could possibly survive. They turned up in cans of corned beef because people were irradiating the beef that they were putting in these tins to then give it a long shelf life. But they then discovered that they couldn't kill these bacteria. They would survive massive lethal doses of radiation. And they have an incredible way of piecing back together their genetic code from multiple copies of their genetic code, which even if they get completely blitzed, they can build a working copy from the bits left over. And you think, when you've got organisms that robust and that resilient, the prospect of us being able to seed life remotely across the solar system is really very high if we're not careful. So this is taken incredibly seriously.
Okay, it is 9:50, The Naked Scientist, with us through till 10 o'clock. Dr. Chris Smith, lecturer at the University of Cambridge. Let's take a listen to another WhatsApp voice note. Joe?
Good morning, Chris. I listened now to your discussion on yawning or explanation. I always say I hate to yawn because I always yawn, and I'm not even tired when I yawn. If someone uses the word, I'll start yawning. if I send a voice note, usually my one friend, they always count how many times I yawn. If I assist my husband with high-level surgery, and I really need to focus, you hold the cord or whatever, I will yawn. And I mean, that's the last time for whatever that you should be yawning. So I've always wondered why it is. Because I hate yawning. If I see patients, I'll sit and yawn, and I feel like they think I'm bored with them. But I'm not bored with them, and I'm not tired. I just can't contain a yawn when it wants to come.
Well, I hope that our programme doesn't make you yawn excessively, but it can be habitual, and it can be that sometimes someone hasn't had enough coffee. People who have an entrenched coffee habit tend to feel very, very sleepy when they don't have enough coffee, and they think there's something wrong with them because they've gone somewhere, and because they've gone somewhere and then out of their normal habitual coffee drinking zone, they don't have as much of the enlivening experience, and so because they've adapted to having that much caffeine on board, they drop off, and it can make them feel very, very tired. Also, environments which are indoors have high levels of carbon dioxide from having a lot of people in there. This also triggers a yawning reflex because it makes us feel or interpret the environment as insufficiently well oxygenated, and we need to breathe better, and it makes us sleepy, so we yawn more. And also, of course, as you've said, you can yawn if people are boring. So as James Watson counselled, try and avoid boring people.
We'll move on to a question then. This one reads, question for Dr. Chris Smith. Why is the longest day in the Northern Hemisphere on the 21st or the 22nd of June, but the hottest weather is 1 or 2 months later or earlier? Dr. Smith?
Well, you have to think about, why is the Earth warm at all? It's warm because we're being bathed in sunshine from the sun, our nearest star, and the arrival of light brings energy to the Earth. But in the same way that when I fill my kettle up and turn it on, I'm providing energy at a very fast rate, but it doesn't instantly boil. Why? There's a delay after I press the button because you've got to put energy into the system to raise the temperature. So as day length increases, you're increasing the rate and the duration at which energy can reach the planet, and therefore you're warming things up. But there's enormous inertia, enormous thermal inertia in the system, which takes time to overcome. Cold water takes time to heat up in the ocean to a temperature where it then makes the air feel much warmer, and so the average takes time to increase. So this is why you don't instantly see hugely high temperatures just because you've got long days. The environment has to heat up, and especially the oceans, which are an enormous energy buffer.
Morning, Dr. Chris. He says it is a water bear. Logan in Edenville wanting to know about Weserbier. I thought maybe he meant Weisserbier.
Those are, yes, water bears. That's the other name for, or the sort of more common name for tardigrade, the organism I mentioned. These are very, very tough, and people realised that they could be exposed to the vacuum of space and survive. And they have done experiments where they've sent these water bears or tardigrades into space and exposed them to space for variable periods of time, and half the population easily survives exposure to very low temperatures and radiation that would wipe out most life straight away.
Okay, then another voice note. No, it's a text note and a message for the Naked Scientist. Why did the universe form the way it did? And could there have been events that could have caused a different outcome?
Oh, absolutely. And this is one of the biggest questions in cosmology. Scientists are trying to understand the nature of the universe. And the problem is we can't see it because it happened 13.8 billion years ago. And there's a period right at the beginning when we are really going to struggle to probe that. So what we do is we look at the universe that we have today. We look at how the universe is evolving and changing today. And we try to understand the processes that have made it look how it is today, with the aim of winding the clock backwards. So you can say, well, we know what we've got today, we know how it's changing today, and what appears to be driving its evolution and its movements. So if we wind the clock back and ask what would it have looked like, or what would have to have started things off to end up looking like that, then we have some idea as to understanding what it looked like at the beginning. There are obviously limits and constraints on all of this, and there is an evolving process going on because the universe is not static. It didn't pop into existence, exist everywhere all at once, and look the way it did today billions of years ago. Isaac Newton thought it did, but Einstein came along and said, well, no, that's not true. And now we've got things like Hubble's insights that we know the universe is growing, but we also know the universe is growing at a different rate at different times. When it was very, very young, it grew very fast for fractions of a second, then it slowed down, now it's speeding up again. We need to understand all of these aspects and model them to then work out how we wind the clock back to the very early days. But there's a whole raft of things that influence the structure and fabric of the universe, and we're only scratching the surface understanding what all these players are, and we can't understand how it started until we understand all of these aspects, which include dark matter, the gravitationally active stuff that holds things together that we can't see, dark energy, the thing we invoke to explain why the universe is growing and growing faster as it grows bigger. We can't understand that, and that accounts for about 70-80% of what's out there in the universe. So we have a lot of explaining to do, and we have a lot of research to do in order to understand what these things are. And until we do know what they are, we don't really understand how it all got started, apart from in a very vague way.
And that, unfortunately, is all that we have time for on this Friday morning. A big thank you, Dr. Chris Smith, lecturer at the University of Cambridge. The Naked Scientist every Friday at 9:30 right here on Views and News.